The story of electricity. Imagine a world without lights, phones, or computers. No charging cables. No electric fans. Not even a single light bulb. Hard to picture, right? But the story of how we learned to harness electricity is filled with curiosity, bold experiments, and a few literal sparks of genius. In this video, we'll explore what electricity really is, how it works, the great minds who discovered it, and how their inventions shaped our modern world. Ready? Let's light up your understanding.
The scene depicts a world before the advent of electricity. Initially, the landscape is shrouded in complete darkness, symbolizing the absence of widespread artificial lighting. Over time, small points of light emerge, representing early human settlements. These lights are powered by rudimentary sources such as candles and oil lamps. The limited and localized nature of these light sources emphasizes the pre-electricity era's constraints. The scene showcases pivotal inventions in electrical technology. These inventions include the light bulb, a fundamental component of electrical illumination. The Tesla coil is also highlighted, demonstrating resonant transformer action. The generator is presented as a key device for converting mechanical energy into electrical energy. Early electrical circuits are shown, illustrating the basic principles of current flow and control. The modern cityscape transforms as night falls, showcasing the impact of electricity. Initially, only a few buildings are illuminated, marking the beginning of the electrical transition. As time progresses, lights rapidly spread, covering entire urban areas. This expansion demonstrates electricity's transformative effect on society. The time-lapse culminates in a vibrant, fully illuminated cityscape. This symbolizes the ubiquity of electrical power in the modern world.
Firstly, let's define electricity. Electricity is the movement of tiny particles called electrons, the ones spinning around atoms. When these electrons flow through a conductor, like a copper wire, they create electric current, the invisible force that powers nearly everything around us. Okay, so in simple terms, electricity is a form of energy that results from the flow of electrons. Okay, let me give you guys a basic concept. Why materials conduct electricity? A material ability to conduct electricity depends on its atomic structure and the freedom of its electrons to move. As a result of this concept, graphite can conduct electricity, while diamond cannot. Graphite's structure allows for delocalized electrons, which can move freely and conduct electricity. Diamond, on the other hand, has a rigid tetrahedral structure with strong covalent bonds, making it an electrical insulator due to the lack of free electrons. Let's look at copper.
Conductive materials, like copper, possess a unique atomic structure that facilitates electron flow. Within this structure, electrons orbit the nucleus and move randomly within the atomic lattice. This random movement indicates the presence of free electrons. Free electrons are not tightly bound to individual atoms. The availability of free electrons is essential for electrical conduction. A conductor, such as a wire, is composed of a dense arrangement of atoms. These atoms contain free electrons capable of movement within the conductor's structure. Applying a voltage to the conductor initiates the drift of free electrons. This electron drift is characterized by a directed movement in a specific direction. The directed movement of electrons constitutes an electric current within the conductor. A simple circuit consists of a battery, wire, and light bulb. Electrons flow from the battery's negative terminal through the wire. This electron flow continues into the light bulb, causing it to illuminate. The electrons then return to the battery's positive terminal, completing the circuit.
There are two main types of electricity, static and current. Static electricity happens when charges build up and suddenly jump, like a tiny lightning bolt when you rub a balloon on your hair. Current electricity, on the other hand, is the steady flow of electrons through a wire, powering your TV, your phone, and even this video. Basic terms used in electricity. To understand electricity, you'll need a few key terms. Charge, the electric identity of matter, positive or negative. Voltage, V, the pressure pushing electrons along a circuit. Current, I, the flow rate of electrons, measured in amperes. Resistance, are the friction that opposes this flow. Power, P, how fast electrical energy is used or produced, measured in watts. Think of it like a river of energy. The voltage is the push, the current is the flow, and resistance is the rocks that slow it down. In 1827, Georg Ohm formulated a law relating voltage, current, and resistance. As seen in the image above, Georg Ohm stated in his law that the voltage in a circuit or material is the product of current and resistance, where V represents the voltage, I is the current, and O represents the resistance. Having said that, let's move forward to the history of electricity. Thales of Miletus. Our story begins in ancient Greece. Around 600 BC, the philosopher Thales of Miletus discovered that when he rubbed amber with fur, it attracted tiny objects like feathers. He didn't know it then, but he had witnessed static electricity. Let's move forward to William Gilbert. Long before modern scientists began harnessing electricity, one man took the very first steps toward understanding it, William Gilbert. Born in 1544, Gilbert was an English physician and physicist who became known as the father of electricity and magnetism. At a time when people still explained natural forces through magic or superstition, Gilbert chose a different path, one based on observation and experiment. He began experimenting with amber, a golden-colored stone that the ancient Greeks had noticed could attract light objects when rubbed. Gilbert tested amber and dozens of other materials like glass, sulfur, and stones, and discovered that many of them could create this same mysterious attraction. He named this effect electricus, from the Greek word electron, meaning amber. From that single word, our modern term electricity was born. But Gilbert didn't stop there. He also studied magnetism, using lodestones and iron to uncover how magnets worked. Through these experiments, he made a remarkable discovery. The Earth itself acts like a giant magnet, explaining why compass needles always point north. Gilbert's work proved that electricity and magnetism were natural forces, not magic, and that they could be understood through careful testing and reasoning. In a world still ruled by old beliefs, William Gilbert's curiosity and scientific spirit sparked a revolution in how we understand nature. His experiments laid the foundation for centuries of discoveries, from simple static electricity to the powerful electrical world we live in today. Okay, let's move over to Benjamin Franklin. In 1752, Benjamin Franklin took his curiosity to the skies. Franklin was curious about electricity. At the time, people knew about static electricity, like rubbing a balloon on your hair, but no one knew if lightning in the sky was the same thing. Franklin had a bold idea. What if lightning is actually electricity? To test his idea, Franklin built a simple kite. He attached a metal key to the string and held the string with a silk ribbon, keeping himself safely away. Then, during a thunderstorm, he flew the kite into the sky. Here's the clever part. As the storm clouds passed overhead, the key started to spark when Franklin moved his hand close to it. That spark proved something incredible. Lightning is electricity. Thanks to this experiment, Franklin invented the lightning rod, a metal rod that safely directs lightning into the ground to protect buildings, which can be seen in the image above. A lightning rod is a metal rod designed to protect buildings from lightning strikes. It works by providing a safe path for electrical charges from a lightning strike to flow into the ground, preventing damage or fire. In the image, the tall metal rod is the lightning rod itself. The wires running down are likely grounding wires, connecting the rod to the earth. The dark storm clouds in the background show the potential danger of lightning. Let's move over to Alessandro Volta and the voltaic pile. Have you ever wondered who invented the very first battery? Let's travel back to the year 1800 and meet Alessandro Volta, an Italian scientist with a spark of genius. At the time, another scientist named Luigi Galvani believed that electricity came from animals. He called it animal electricity. But Volta wasn't convinced. He thought the electricity didn't come from the animals at all, but from the metals touching them. To prove his idea, Volta decided to make electricity himself, using Nothing but metal and salt water. He built what became known as the voltaic pile, the world's first battery. He stacked discs of zinc and copper, one on top of the other, and placed pieces of salt water-soaked cloth between them. When he connected wires to both ends of the pile, something amazing happened. A steady electric current flowed. For the first time in history, electricity could be produced continuously. Volta had proven that electricity could be made chemically, not just by friction or from living things. His simple stack of metal discs changed the world. It became the model for every modern battery we use today, from the one in your phone to the one in your car. And to honor his discovery, the unit of electric potential was named after him, the volt. Let's move forward to Michael Faraday and his role in harnessing of electricity. In the early 1800s, electricity was still a mystery. Scientists could make sparks and small currents with batteries, but no one knew how to produce electricity easily or continuously. Then came Michael Faraday, a self-taught English scientist with endless curiosity. Faraday wanted to understand how magnetism and electricity were connected. His goal was simple but ambitious: to create electricity from motion. He began experimenting with magnets and wires. In 1821, he discovered electromagnetic rotation, showing that electricity could make a magnet move in a circle. That was the first step toward the electric motor. But his greatest discovery came in 1831. Faraday found that when a magnet moved through a coil of wire, it produced an electric current. This was a breakthrough. It proved that motion and magnetism could create electricity. He called this process electromagnetic induction, and it became the foundation for every electric generator in the world. Faraday's simple setup, just a magnet and a coil, became the starting point for the power stations, motors, and generators that light up our cities today. He didn't invent the light bulb or power lines, but without his discovery, none of those things would exist. So, the next time you switch on a light or charge your phone, remember the man who made it all possible, Michael Faraday, the man who learned how to harness electricity. Okay, let's move forward to James Clerk Maxwell's role in harnessing electricity. James Clerk Maxwell, born 1831, was a Scottish physicist and mathematician. He didn't invent electrical machines or devices directly, but he did something even more important. He discovered how electricity and magnetism are connected, and how light is part of that same system. His work laid the foundation for almost all modern electrical and communication technologies. Maxwell studied the work of earlier scientists like Michael Faraday, who discovered that changing magnetic fields could produce electric currents, electromagnetic induction. Faraday's experiments showed what happened, but he couldn't explain it mathematically. Maxwell translated Faraday's ideas into a set of mathematical equations, now known as Maxwell's equations. These 4 equations describe how electric and magnetic fields are created, how they interact, and how they can move through space as electromagnetic waves. Using math, Maxwell predicted that these waves would travel at the speed of light. That meant light itself was an electromagnetic wave, a huge breakthrough. Wasn't trying to build practical devices. His goal was scientific understanding. But his theoretical work made practical electricity, wireless communication, and modern physics possible. Let's move forward to Edison, Tesla, and the War of Currents. By the late 1800s, scientists and inventors were trying to turn electricity from a laboratory curiosity into something that could power homes, factories, and cities. 2 men became the leading figures in this transformation: Thomas Edison and Nikola Tesla. Their rivalry became known as the War of Currents. Thomas Edison, direct current, DC. Edison was one of the first to develop a practical system for generating and distributing electricity. He invented devices like the light bulb, electric generator, and power distribution systems. Edison used direct current, DC, electricity, where electric charge flows in one direction. He built the first power station in 1882 in New York City, the Pearl Street Station, which supplied electricity to nearby homes and businesses. His DC system worked well for short distances. Edison showed that electricity could be generated on a large scale and used to power lighting and machines, proving that cities could have electrical power networks. Nikola Tesla, alternating current. Tesla was a brilliant inventor who developed the alternating current, AC, system, which became the foundation of modern electrical power. Tesla designed AC generators, transformers, and motors. In AC systems, the current changes direction many times per second, allowing it to travel long distances efficiently. He partnered with George Westinghouse, who funded and promoted AC power. Tesla's system proved that AC power could transmit electricity over long distances without losing much energy, something DC couldn't do. In 1896, Tesla and Westinghouse built the first major AC power plant at Niagara Falls, successfully sending electricity to Buffalo, New York. Tesla wanted to create a system that could deliver cheap, efficient power to everyone, not just people living near power stations. He believed electricity should be a gift for humanity. The War of Currents. Edison, DC, and Tesla Westinghouse, AC, became rivals in what was called the War of Currents. Edison claimed AC was dangerous, even staging public demonstrations to show it could kill animals. Despite Edison's efforts, AC power eventually won, because it was cheaper and more practical for supplying entire cities and regions. The War of Currents proved that alternating current was the best way to distribute electricity efficiently, a system still used today. From amber to power plants, the story of electricity is the story of human imagination. How we turn sparks of curiosity into the energy that fuels our entire world. Every flick of a switch, every charge of your phone, traces back to centuries of discovery, creativity, and courage. Electricity connects us all, in every light that shines, every machine that runs, and every idea that sparks innovation. Thanks for watching. If you enjoyed this journey through the story of electricity, hit like, subscribe, and stay tuned for more science stories that illuminate our world.